Density is perhaps the most fundamental measurement you can make about an object in the solar system. It's the one that you measure to first get an idea of what that object might be made out of. And a lot of effort has been put into measuring not just the density of planets, but densities of satellites. Densities of satellites are hard. You can only find densities of things that have something going around them or perturbing them, but we've sometimes had spacecraft go to satellites. We have density measurements now of things like asteroids. We'll talk a lot about these objects in the next unit in the class, and these come because those asteroids have satellites. But I'm going to talk now just about the planets themselves. This is a picture that shows the planets with their correct relative spacings and their correct relative sizes, but you can't show relative spacings and relative sizes at the same time because you would end up having little dots that you couldn't see at all. So the sizes are greatly exaggerated, but they at least are correct in a relative sense. And you very quickly notice just by looking at this that we have some major differences going on in the planets just by size. There are these tiny ones here in the interior all grouped together. There are these two that are more or less the same size that are here in the middle part of the solar system. And Uranus and Neptune, although sometimes we think of them as the giant planets like Jupiter and Saturn, they're actually quite a bit smaller and quite a bit less massive. And we'll see in a minute that they clearly have different properties. If you were to divide the solar system into parts, simply looking at this, you would probably divide it into these three parts, although maybe you'd be tempted just to do gas giants and terrestrial planets, as we call them. But you would really know that you were onto something when you put the densities of all these objects together with their sizes and locations. First thing I want you to look at is the terrestrial planets. They all are high density. Remember what I said about densities? I said that the density of rock is something like 3 grams per centimeter cubed, and ice, or water, is something like 1 gram per centimeter cubed. And iron, another main component, is close to 8 grams per centimeter cubed. And you can quickly see from these high densities of Mercury, Venus, and Earth that they probably have something more than just rock in them. If we look on the surface of the Earth, and I go around and pick up a rock, it's going to have a density somewhere around 3 grams per centimeter cubed. But there is heavier material underneath. And there's enough heavier material underneath that it can't just be due to the compression of these rocks. That's one of the many different reasons we know that there is a core, higher density, and iron in through there. Venus and the Earth have very similar densities. They have very similar sizes. Mercury is actually quite a bit smaller than Venus and the Earth, and yet the density is as high. That means there's not nearly as much compression on the inside. That means to have the same density as Venus and Earth, there must be even more high density material. And it's true. We know that there is a substantial iron core inside of Mercury, much bigger relatively than that of Venus or the Earth. Let's move out here to what the point here was supposed to be, which is Jupiter. 1.3 grams per centimeter cubed. And it's huge. Whatever it's made out of is highly compressed on the inside. So the material it has must be much less than 1.3 grams per centimeter cubed. Is there any rock? Well, certainly not much, if any. Iron, no hint of it. Ice? Well, even ice would be compressed so much that it would have a higher density than this. This is a good indication that Jupiter is almost entirely made out of gas. Very much like the Sun. The Sun is an interesting one to look at too, 1.4 grams per centimeter cubed. It is, of course, entirely made out of gas, and it's compressed because it's so huge. But there's another interesting thing going on with the Sun. Because the Sun is so hot, it expands and the density goes down. There was some speculation early on that maybe this 1.3 grams per centimeter cubed was because Jupiter was indeed made out of the same materials as the Earth, but that it was super hot on the inside, just like the Sun, and that heat caused it to expand and be less dense. People tried to measure the heat coming off of Jupiter for a long time. If you remember, we talked about that same process on Mars in the 1950s. People had tried to measure it coming off of Jupiter much earlier than that, and one way they tried to do it is that they would take a telescope and point it at Jupiter, and inside the telescope, there's a mirror, light comes to a focus at a point right here, and they would put a small disk that would be deflected by the pressure of the heat, the emission, thermal emission coming through there, and they would try to measure that deflection. No successful measurements were ever made, but the way they calibrated it was with candles. They would put candles at certain distances away, and they would write papers about how they lit the candle, waited for the flame to develop, and they developed this entire thing called standard candles And I'm just saying this because it's funny for any of you who follow astronomy. Standard candles is the term that astronomers use all the time for anything in the universe that has a brightness that you know how bright it is, and therefore if you put it further away, you know how far away it is because you know how bright it intrinsically is. I've heard that phrase all of my astronomical career. It never occurred to me that actually they started these out as candles. The first standard candles were candles that were standard. In any case, the temperature of Jupiter was eventually measured the same sort of way that Mars was measured, and it was found that it's quite cold, something like 130 degrees Kelvin. Certainly so cold that this 1.3 grams per centimeter cube mean that Jupiter has to be predominantly made out of gas. While we're here, let's look at the other giant planet, Saturn, even lower density than Jupiter. Now, it's not as big as Jupiter, you can't quite tell that, but it's not as big as Jupiter, so there's less compression, but still the lower density of Saturn is a bit astonishing. But the more interesting thing, I think, are these two outer giant planets, Uranus and Neptune, with densities of 1.2 and 1.6 grams per centimeter cubed. Now, you might argue that 1.2 is kind of close to 1.3, but Uranus, now you can see, Uranus is so much smaller than Jupiter that there's much, much less compression going on here. So there are significantly more dense materials in Uranus than in Jupiter. And by the time you get to Neptune at 1.6, there is a ton more. And so we actually often call Uranus and Neptune ice giants, with the idea that a lot of their interiors are things like actual ice or liquid water or some weird high pressure combination of the two of those. We'll talk about that more in detail. We'll go back now and examine what this 1.3 grams per centimeter cubed for Jupiter's density tells us about our central question, what's on the inside?